In a recent podcast interview, Elon Musk said that the AI needs to increase its intelligence density per gigabyte by 2 orders of magnitude to achieve a certain unidentified platonic maximum of efficiency. A pundit of artificial general intelligence like you and I has two options at hearing this. Proclaim that there has been no acceptable measure of intelligence identified after about 100 years of trying, and given the absence of the numerator in the intelligence per gigabyte, proceed by speculating about measures like stupid per kilogram or unrestrained per hour, or try to extend the abortive line of thinking of the villain/genius in question to arrive at a more intellectually satisfying conclusion. Choosing the latter, I'm Alex Chadyuk, and this is AGI. Listen every Monday morning on your favorite podcast platform. One approach that can be used to make sense of Mr. Musk's density metric without coming up with a full-fledged measure of intelligence is to rely on a comparison with an existing intelligence system like a self-driving vehicle taken as a reference. We can create a previously unseen simulated video of a challenging highway scenario, like, for example, an unfolding car collision, and define a set of correct behaviors that a vehicle should perform in this scenario, like safe braking and avoidance maneuvers. In the AI jargon, such test is called an eval, short for evaluation. So now we can take the reference vehicle's neural network and see how it performs on this eval, for example, at which point in the video sequence the neural network decides that this situation is dangerous and initiates corrective action. And now we can take the behavior of the reference vehicle as a benchmark. Imagine that you unfurl the video sequence on a wooden bench in the shed, pull out a pocket knife and cut a mark in the bench at the point where the reference vehicle starts to brake. This is our benchmark. Now, we can use this same video to test the new neural network that we made smaller so that it can run on cheaper hardware, for example. There are a number of ways to make an existing neural network smaller. You can take the original neural network and simply reduce the numerical precision of the parameters that define the response of each individual neuron. These parameters are usually 32-bit floating point numbers, which you can roughly think of as 9 decimal digits of precision. We can reduce that to 24 bits, or about 7 decimal digits of precision, but keep the number of parameters and the overall architecture of the neural network, that is, all the connections between the neurons, the same. In the AI world, such model reduction is called quantization. Another way to reduce the model size is to use the output of the old neural network to train a smaller neural network with fewer neurons in it. Such training is called distillation. Now we can run the new neural network on the cheaper hardware and, with some luck, discover that it matches our reference benchmark. The new neural network starts braking at exactly the same mark in the video sequence. So we managed to match the self-driving intelligence of a new model with the intelligence of the old model. Because the new model demonstrates the same level of intelligence but uses less memory to store its parameters, we can say that the new model has higher intelligence density per gigabyte. If the old model parameters took 10 gigabytes of space and the new ones only take 7, we have increased the density of intelligence per gigabyte by about 43%. I did say earlier that we did all this without defining a new intelligence metric, but this is not entirely true. We did define an eval, which included both a test video and an explicit definition of what behavior we expect in the proposed scenario. For example, we would not call acceleration an intelligent behavior when the optimal behavior for this test vehicle was braking. But in another scenario, like a falling tree, an optimal behavior may well be acceleration. We had to provide a justified opinion on that, which contributed to our operational definition of intelligence. In other words, although we did not make any claims about what a vehicle intelligence is, however, we did specify a behavior which, when exhibited by a vehicle, is, in our opinion, a symptom of intelligence. We avoided the need to measure the difference in intelligence between the two models by stacking our little thought experiment in such a way that the benchmarks of both vehicles matched, which is a valid trick when we do not have a good ruler to measure the difference in intelligence. But the match of the benchmark was not fully agnostic. As I said, it was implied by a heavy set of preconceived assumptions about the optimal behavior in this situation, including the definition of the criteria that are used for defining what optimal means in this instance. For example, is changing the audio volume an irrelevant behavior in this situation? Or is it something that can help attract the human driver's attention to the dangerous situation on the road and contribute to the overall optimal outcome? As you can see, there is nothing trivial about a density metric proposed by Mr. Musk, and it by no means replaces the need for a better definition of what intelligence is and isn't, even if the definition that we can propose at present is operational at best. We will continue to explore this idea in the next episode. Please like and subscribe. Until next Monday, my friends. I am Alex Chadyuk, and this is AGI.